fan, we have Wi-Fi enabled AC, so they can be made part of the, you can say, wireless network, and by using some interfaces like Alexa by Amazon or some similar kind of interface, they can be controlled. So just by using voice commands, we can control the devices, and maybe in the near future we will find, you can say, lot many applications. But when we talk of, you can say, such kind of large number of devices, huge traffic is being generated. If you want to remotely control such devices, for example, sitting in the office, I want to put my AC off at the home. This means the communication will be done through the wireless link from my office to the home, and hence there has to be, I can say, strong communication pipe or bandwidth available from one end to another. Huge volume of data will be generated. For example, if the vehicles which are part of the highway, they are sending information to an individual, so a lot of traffic is generated. In traffic means in terms of data volume. So how to take care of this? So therefore there are complexities in terms of handling this data, how to store this data, how to communicate this huge volume of data, even how to process the data. So maybe rather than storing the data in raw form, we can compress it, but compression techniques, they will be different. For example, such kind of data will be big data. Big data is generally, say, structured data and unstructured data. It is not necessarily big in volume. There may be structured data which is much bigger in volume as compared to say what we call as, you can say, big data. But the difference lies that what is the structure of the data. There may be some RDBMS that generates huge volume of data, but still it may be structured. There is well-defined structure. So it is not termed as big data. Big data is, say, generated by different channels. For example, we talk of Twitter, we talk of Facebook, we talk of, you can say, such kind of sensors, we talk of say vehicles, etc. So they are generating in their own format, and this leads to big data, and this big data has to be handled. So a lot of issues are there that how to take care of such deployments. Now, whether we talk of IoT or we talk of wireless sensor networks, say underlying technology is that it is a heterogeneous kind of scenario, and different types of devices are there. So some devices are constrained in resources, so there are issues. I can say that devices, already we have talked that they are constrained in resources, specifically battery processing, then even communication interfaces, they are not so strong because we use radio technology though. So a lot of constraints are there, and similarly constraint is there in memory. If you talk of sensor node, the size is very small, and maybe the processing capabilities of few megahertz rather than being gigahertz. Similarly, batteries, say generally 2 joule of say backup initially, and later on it will reduce with the passage of time. And then memory is, it may be few megabytes rather than we talk of, you can say, gigabyte, or we talk of terabyte kind of storage for the sensor networks or for the sensor. So therefore the resources, they are constrained. Then variable channel capacity, because the network is heterogeneous in nature and different types of devices are there. If you talk of IoT, it will be integrating different technologies. On sometimes we be available with the strong backbone of, we can say, fiber, which is having, say, few Gbps capacity, whereas on some places we may have, we can say, few Mbps capacity. So therefore the bandwidth is varying in nature, and we have to address different networking parameters. For example, what should be the size of the transport data unit, or what should be the size of the packet that can be transmitted or which can be communicated from one place to another. So we have to take care of the bottlenecks which are formed in different parts of the network. Bottlenecks may be due to bandwidth, or even they may be due to processing capability of the individual intermediate nodes. For example, if we talk of such kind of cooperative networks, then intermediate nodes, they have to process the data, they have to take some decisions about the data, where to route it further. So in between, buffering may be required. If buffers, they are not larger in number, so such kind of nodes, they become bottleneck in nature, and hence these bottleneck issues, they are to be taken into account, and we have to say propose solution which is applicable to varying capacity, or which is applicable by taking into account different parts of the network. Then in network processing, there may not be the case that we are transmitting data in raw form. For example, if there are, you can say, some thousands of sensor nodes, they are deployed, or thousands of vehicles are there, then packets generated, they need to be communicated from one place to another. If we communicate them as it is, then huge traffic is generated. There are techniques called in-network processing, where in between we can process the data. So simple examples are like, we can, for example, suppose we want to study what is average temperature in particular part of the campus. Then rather than sending, say, raw data values for the temperature, whenever data is communicated through a particular node, it will be receiving data from multiple nodes. So there we can find out the average, and then that single value can be communicated, rather than communicating, say, 20 values which are obtained from the neighbor. Similarly, at next higher level, maybe next 50 values are obtained. So rather than communicating 50 values, we will be communicating only single value, say average temperature. Similarly, it may be say maximum temperature. So rather than transmitting all the values, say 100 values are there, we will find out the largest one, that is the maximum one, and it will be communicated. So this kind of processing is called in network processing, and it is useful in such kind of scenarios where huge volume of data is generated. So rather than communicating raw values, we will be doing some processing at intermediate nodes, and hence it is called in-network processing, so that volume of data to be communicated is reduced, and according to that we can optimize the resources of the network. Now there is again well-established research that computing consumes less energy as compared to communication. For example, if you want to process 100 bytes of data, then processing 100 bytes of data consumes much less energy as compared to communicating those 100 bytes. So rather than doing some processing, for example, now if we combine data from different nodes, do in-network processing, maybe thousands of data packets, each comprising of, say, 100 byte is there, so that can be processed and single data packet is generated. So we will be communicating this single packet. Now some energy will be consumed for doing in-network processing, but that you can say energy consumption will be less as compared to communicating those raw values, and hence we can save large in terms of battery by doing computing and transmitting small volume of data. Similarly, if we talk of, you can say, multimedia data, where images are there, audio or video is there, we can identify that this is the data to be communicated, but the complexity or issues which are involved in identifying that this data is more useful is much more complex as compared to say conventional applications where scalar data like temperature, pressure, etc., those values are used. For example, given, say, 100 photographs, how we identify that out of these 100 facial photographs, the best one is first photograph or other. That is how to select the best one. Similarly, suppose visual sensors are there which has captured images from particular portion of the road. Now how to transmit only the best image. So therefore we have to go into internal details that how the images are represented and how we can identify say best one for the purpose of communication. So best one may be identified depending upon the scenario. It may be single image or it may be multiple images. For example, rather than sending say 100 images, can we select 10 best images which can be transmitted. So how to say select those 10 images which are, you can say, more useful or which contain most of the information. So it is a research, you can say, domain that how to do it, if specifically if you talk of, you can say, sensor networks or IoTs. So whatever you can say technique of caching, I will be talking, I have taken into consideration the, you can say, visual data which is based upon images. So how better images we can identify so that in-network processing can be done, and out of say given hundreds of images we can select the best one, and that can only be transmitted. Now we are talking so much about energy. So energy, whether we talk of, you can say, sensor networks or we talk of any conventional network, is generally used for capturing data. So in case of sensor network, it becomes sensing, and it is consumed for communication and for doing some computing. So these are three domains where energy is consumed, and we have to optimize say these domains in order to reduce the energy value that is consumed, because the battery backup available with sensor nodes is limited, and how we can reduce energy on account of these domains so that overall energy is reduced. That way we can prolong the lifetime of the network. So simple scenarios may be there. For example, if you want to reduce the energy for sensing, maybe we can you can say think of, you can say lower resolution, that if some images are to be captured, maybe the resolution can be reduced. Similarly, if you talk of, you can say, sensing some scalar data, we can think of, you can say, sampling rate, that rather than sensing data say every 3 seconds, we can think of, you can say, sensing maybe after 20 seconds or even after 1 minute, depending upon the criticality of the environment. Even sampling rate may be higher. For example, maybe 5 sensing data after 5 minutes may be sufficient in some applications. So therefore, rather than making it a, I can say, constant value for different types of applications, it may be specific to the application scenario, and hence we can reduce the volume of data that is generated. Similarly, volume of data can be reduced, so thereafter it has to be processed. So we can do some sort of, you can say, processing. We can think of, you can say, simple techniques. For example, rather than talking of some lossless techniques, processing techniques, we can think of some lossy techniques, so that we can compromise with some error, and that compromise again depends upon the type of applications or the underlying environment we are dealing, but still we can tolerate some errors wherever it is possible depending upon the application scenario, and hence we can do less processing or less computing, and volume of data can be reduced. Then sensor nodes, they are, I can say, having fixed hardware, so can we think of some reconfigurable computing in the future, so that sensor nodes, they can be realized by using some reconfigurable hardware. For example, we can think of using the same hardware for the purpose of doing say useful activities like computing, communication, then doing some or camera related activities. So same hardware can be configured efficiently to work as per the requirement of the you can say situation. So therefore the given hardware has to be configured or has to reconfigure as per the requirement. So that way maybe this kind of future opportunities are there, that given the smaller size of the sensor nodes or the nodes which are using, how they can be configured as a, you can say, useful device depending upon the situation. Then communication, how data can be, you can say, communicated. Effective communication, as I told, that we have to reduce the volume. So volume of data can be reduced in order to reduce the energy consumption. So we can apply some compression technique, and also I gave example that how data processing can be done as part of network processing, and we can reduce the volume of data to be transmitted, and that way I can say less number of packets and smaller packets, they are carried from one place to another. Therefore, energy of the sender, intermediate nodes, as well as at the destination will be consumed less. So therefore, it will be having effect on all the parts of the network, and hence we can save on these parameters. Because of the next line, lifetime is a function of sensors remaining energy. So different sensor nodes are there, whatever you can say, they are balance energy available, and then lifetime of the whole network is dependent upon this parameter. So we have to increase this residual or remaining energy. Larger the value of residual energy or remaining energy for different sensor nodes, longer the period for which it will last, and hence we can apply different energy efficient techniques, because we cannot reduce this consumption through existing hardware techniques, and therefore we have to go for software techniques. So we have to think of, you can say, better software tools or better software protocols, so that energy consumption can be reduced. And energy is the parameter because it is not possible to recharge. It may not be possible to replace the battery. Nodes may be self-powered, because nodes, they have to self-heal themselves, and hence they have to take care of, we can say, whatever you can say, battery power available with themselves, and whatever you can say available, they have to continue with that battery power. So depending upon the load over the network, the node can take some decision whether it has to participate in the routing, it has to participate in network processing. So depends upon the node, and we have to embed some intelligence or intelligent routines in the node, so that they can function as per their available capacity. So again, the parameters that I have discussed, they are reiterated here. Communication is often the most energy intensive. So we talk of, you can say, sensing, communication, and data processing, three parameters or domains where energy is consumed, but communication is the most costlier in terms of energy consumption. And in some applications, for example, images or multimedia data, even sensing may be energy intensive. So how to optimize it? So I gave example that we can reduce the intensity or resolution with which data is captured, we can reduce the data sampling, etc. So these mechanisms. Now data sampling may not be constant, it may be adaptive. For example, if we talk of visual sensors, now there may be some motion sensor activated, and it will be sensing the data. And if there is no motion, then even sampling rate may be much higher. For example, maybe for half an hour there is no movement or there is no disturbance, then there is no need to capture the frame by using a visual sensor which may be focusing on some door or some window, etc. Similarly, so the requirement is that we have to think of, you can say, energy efficient or energy conserving protocols. So a lot of research is going in this domain, that how to prolong the lifetime for longer period by applying, you can say, different energy conserving or energy efficient protocols at different levels, whether we talk in terms of routing, we talk in terms of resolving the, you can say, communication, say, disturbance at the level of MAC layer, or we talk in terms of transport layer, or we talk at application layers. So different levels or layers, we have to be sensitive about energy efficient protocols or techniques. So I gave you background that such kinds of deployments may be there where huge large number of nodes or huge uh, 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 deployment density may be there for sensor nodes. Now these sensor nodes, they may be of heterogeneous or homogeneous natures, and we have seen underlying applications that they may be part of IoT, they may be part of, you can say, vehicles on the highway. So sensor nodes, they may be of different types and different capacities. Now resource constraints still, but whether we talk any, you can say, kind of environment will be remaining there. So one of the resources is memory that has to be optimized. So rather than, you can say, talking of using the memory in isolation, can we think of some techniques where accumulated memory or cooperative memory can be used so that we can say optimize the resources and data availability can be increased at the nodes. Similarly, it also leads to, you can say, better use of energy and better use of, you can say, computing and communication parameters, so that overall energy consumption can be reduced, and hence the overall protocol or the scenario will be energy efficient, and that way we can think of, you can say, using such underlying technologies, whether IoT, vehicles or sensors, for longer period. So coming to the theme of my talk, caching. So in general, caching is not necessarily, we can say, faster piece of hardware where data can be stored as per the requirement of maybe the processing unit or as per the requirement of the processor. This is, you can say, one specific type of caching where hardware piece is sitting nearer to the user, that is in this particular the CPU, and it will be able to, say, get and store data at faster speed in that hardware piece. So generally we talk of L2, L3 caches in terms of hardware, but in general caching is a technique where frequently accessed data items or data that has already been used by the application are generally stored closer to the requester than to the original source or later reuse. So idea is that we have to store data closer to the user so that later on, whenever requirement is there, that data can be reused. For example, if you talk of web caching, you might have experienced that if you are part of campus, some research paper has been downloaded or some even video clips have been downloaded in the campus, and then those data items, they will be, you can say, available immediately as you try to download them. So the initial request will be going to the faraway resource. For example, some data, research paper or video clip or maybe lectures recording may be lying in some university data center in USA. So first time if you download it, it will be coming from that resource. Next time if someone tries to access from the campus, the data will be obtained from nearby storage. So nearby storage, it may be at the boundary of the campus, that is in terms of proxy servers. It may be as part of the, you can say, browsers or somewhere. So different hierarchical levels are maintained in order to store the data, and accordingly there is concept of what we called as, you can say, proxy caches. So you might have experienced that they work very faster. So can this kind of scenario be extended for IoTs or for wireless sensor networks. So the concept of caching equally applies in these environments. Similarly, this kind of concept applies in case of operating system in terms of databases. Here we talk of, you can say, data replication, we talk of fragments of data, etc., which are to be cached. So this scenario, in addition to being applicable in hardware where processor requires the data for faster processing, is extended to distributed environment, to databases, to operating systems in proxy caches, and same way it can be extended to technologies like mobile ad hoc networks or wireless sensor networks. Even such kind of techniques or tools, they are available on our mobile phones. Can we think of technology that data can be anticipated, or my mobile phone can predict that this is the future requirement of data, and as and when there is strong connectivity, it will be downloading the data so that it can be used later on as and when required. So that way data has to be proactively cached, or we have to prefetch the data. And hence, how to identify or how to predict that this is the data which is going to be useful in the future applies to caching, to prefetching. For example, whenever we talk of, you can say, conventional caching techniques, there also we take a decision that, okay, this data is more useful as compared to the data which is already lying in the memory. So we go for memory, you can say, cache replacement techniques. So such kind of replacement techniques, they are also to be applied in wireless sensor networks. Now we talk of, you can say, maybe some decision has to be taken whether the incoming data has to be cached or stored or not. Now there has to be a mechanism of what we call as, you can say, cache admission control. So when we talk of caching, the issues related with admission control, replacement, then even handling, you can say, consistency, that whether the data is consistent or it is still fresh data, it has not become stale or obsolete, those decisions they are to be taken. So given any scenario, any kind of environment we consider, objective is to cache the frequently accessed data items at device to improve performance of database queries and availability of data items for the query. So because ultimate objective of storing the data is to, you can say, respond to the query, to respond to the user request. Now user request may be the request from particular sensor node, or it may be, you can say, a request from particular even bigger machines, mobile phone, from laptop, etc., which are sitting as part of our site world, or it may be from vehicles which are part of VANets, etc. So any kind of user we talk of, objective is that how to provide faster service to those users. So for that we can go for the use of cache. Excuse me. Hello.
Yeah, yes, sir.
Yeah, should we take break as per your schedule, or I have to continue? No, tell me.
Sir, it's up to you. You can decide if you want break of 10 or 20 minutes, then we can continue, or you can continue.
You can continue the session, no problem. It's
okay.
up to you.
Okay, so till what time it has to be continued?
So 12:30 or 1, as you say.
Okay, okay.
12:30 I think will be better.
We do one thing. We take, say, some 10 minutes break, or should I continue? Whatever you tell.
So let's have a 10 minutes break.
Okay, okay. So that
participants will also.
Yeah. So 10 minutes break. At 11:45 we again start. Okay.
Sir, there is a query from the participants that they want to share some. Maybe they may have some queries. What is the better way to deal with? Should we deal with them at last, at end? Interactive session, so that if some of the students may have queries, so that we can sort out them.
I think the better will be they can note down their queries, and at the end we can address them. Otherwise,
I have already shared with them. You just note down all your queries. I will request to the esteemed guest at end that have a interactive session for some for few minutes.
Yeah, so at the
Okay.
end we can have that kind of discussion so that in between, otherwise it will break the continuity.
Yeah,
And
because there are a lot of participants are in huge number, so it will
yes,
be difficult for to have in between
yes.
this.
So in the last for maybe 10-15 minutes, we can have those kind of discussions.
So all the colleagues, we are having a 10 to 15 minutes break. So after then we will join by the sir.
Okay.
Okay.
Hello.
Yeah, sir. Welcome
Yeah.
back, sir. Welcome back,
Okay.
sir. You can start, sir.
Okay. Okay. Thanks.
Okay. I request everyone to be online because the sir has once again is going to start the session.
Okay. So we discontinued from this point. I was talking about what caching is and how the scenario or the concept has been extended from hardware to other domains like operating system, databases, distributed environment, and presently we talk in terms of maybe ad hoc networks, wireless sensor networks, IoTs, even in terms of vehicular ad hoc networks or intelligent transportation system. Even scenario is being used in mobile phones nowadays, and some companies they are working that how mobile phones they can exploit say ad hoc kind of communication so that calls they can be routed without going to service provider. So it will be working some sort of, you can say, local intercom facility within the campus, like we uh, talk in terms of technologies like voice over Wi-Fi or say uh, how IP can be realized over wireless networks. So anyway, now predictive caching, as I was talking, how we can anticipate the future requirements of data so that data automatically preloads onto the cache for possible future uh, use or to satisfy possible future requests. And there is equally important issue related with the replacement, because if we talk of sensor nodes, they are having limited memory, so decision has to be taken that which data item should be dropped when cache is running out of space to accommodate a new item to be cached. Now, whatever is a new item coming or new data coming, it may not be so important. So we have to take a decision whether they should be stored or not. Maybe whatever you can say data which is already lying in the memory is important as compared to this new data. So we have to take decision accordingly. And if new data is important as compared to some of the data items which are already part of the memory, we have to identify what is the item that is uh, victim for replacement. So here we have to think of, you can say, some say mathematical models. If we focus upon conventional techniques, then we talk or we you can say have seen techniques which are based upon single function. For example, it may be uh, part of you can say the time that is be used you can say least recently item as a victim for replacement. Then it may be factor of some size, it may be factor of some other parameter. Can we think of technique which is dependent upon multiple parameters so that we can take more optimal decision? So that is the objective of this kind of research. Now, here the caching has to be cooperative, because we have seen that nodes they are constrained in terms of resources. So therefore, a caching node, that is a node where data has been cached, not only serves its own data request but also request from others. So therefore, it is not the case that data is stored and it will be used by that particular node only. No, when we talk of cooperative networks like WSN, then data has to be shared by neighbors also, and hence the cooperation has to be extended. But this should be again taking care whether whatever you can say data shared is uh, genuine, or it may be even stale data, or there may be some security compromises which are part of this data packet. So the nodes they should be careful enough that whatever you can say data being used from neighbors, whether it is worth believable, or we have to do some post-mortem of that data so that we can check it for you can say security or some other intrusion related threats. And of course, then vice versa is that a caching node not only stores data of its own nodes, own needs, but also as per the you can say requirement of other nodes also. And shorter path, less expensive links and lower links of route, breakage, etc. they are to be used. So whenever you can say data is coming, rather than taking longer routing path, we have to take into consideration the shorter path. Then even there may be dynamic nature of costs involved for transmission of data, which is almost similar kind of scenario in conventional networks also. So there we take optimal decision. Maybe some of the routes they are not, we can say, cost effective, and hence we have to plan cost effective routing so that the cost involved in getting data at particular location is optimal or it is lower. So caching can reduce time and therefore delays, jitter, etc. These problems they are reduced. For example, if you talk of, you can say maybe continuous monitoring of some hostile environment for the purpose of say studying rainfall, landslides, tsunami, etc. In that case, a huge volume of data is generated, so useful data can be saved and it can be used in future also. So delays they will be saved and we can take strategic decision at earlier stage, and hence alarms and predictions they can be raised accordingly. Then of course it will save energy because of communication, because of sensing, because of computing being involved, and if data is stored from local or from nearby nodes, it will save on these parameters. So applications may be in the warfare, it may be in regular ad hoc network, or we talk of even in case of mobile phones that if we are sitting in a location where some latest trends of data they are coming, it may be related with some simple applications like cricket score. So maybe every time the score is coming, if from backend server, the delays may be higher, and if we try to play it in almost real time as a video, then some mobile phone might have downloaded it, and maybe the nearby phones they are using the same downloaded clip. So that way sharing can be done, and we are able to save on different parameters, whether computing, communication, memory, energy, etc. So if we talk or extend IoT paradigm in detail, then generally it can be divided into 3 layers: lower layer, then middle layer, and higher layer. Lower layer comprises of, we can say, devices which are at the end. So it relates with, you can say, things layer, or the devices which are at the user premise. Different devices may be, say, different types of sensors. It may be camera, it may be some mobile vehicles, etc. So they fall what is called things layer. Now their storage capacities, their processing speed, etc. Are limited, and they can work in cooperation with each other or other devices so that the resources they can be shared. And hence the caching mechanism, whatever we are discussing, can be applied over these devices also. Even if you go to middle layer, there we talk in terms of some high capacity devices. For example, there may be some edge node or computer, so they have, we can say, larger storage capacity, etc., and data may be cached here, so that if there is a query from outside world, they can serve those queries. So data may be cached at this premise also. And on the top we have, we can say, cloud data center, so they have huge capacities, and data has to be routed or processing has to be done. So it may be two-way communication. For example, if some decision are to be taken at edge layer, then maybe their capacities in terms of processing of data are not so smart, and they have to depend upon cloud layer. So data will be sent from this layer to cloud layer, it will be processed, and accordingly the results, they are communicated back to the you can say edge layer, and accordingly they may publish those results to the outside world, or they can take some strategic decisions. So caching, etc., that also applies at this layer. For example, here we have, we can say, edge node and using some data cache. So concept is that data can be stored temporarily so that the future requests or future demands, they can be satisfied. Now, if we talk of, we can say, this kind of network, so of course they are cooperative because they have to depend upon their neighbors, and hence the cooperation has to be extended. So cooperative caching will be helpful because the nodes they are having, if we talk at, you can say, layers which is related to sensor nodes, that is the things layer, then data has to be cooperatively shared because the constraints are there in terms of storage, and hence we have to use storage as accumulated storage rather than individual storage. Accumulated storage means maybe 5 neighboring nodes or maybe 100 neighboring nodes. They are storing different types of data items, so that way the total storage capacity increases, and their future demands can be satisfied not only from local storage but from neighbors also. So that is, you can say, a pure example of cooperation and how it will be effective in giving as a accumulated larger storage. Now, as I was talking, that this kind of research work is applicable in various environments like operating system, database, web distributed system. So we have concept of, we can say, proxy caches, we have caching, and even mobile cellular network. We talk in terms of maybe the base station or access point, and different nodes, they are communicating through access point, and they have stored some data. Now this data, with the passage of time, may become invalid. For example, data may be related with the weather, you can say, situation. Then maybe after every 20 minutes, data will become invalid. Similarly, there may be some other application scenario. It may be cricket score. So in that case, even data may become invalid after every 5 seconds or every, you can say, 2 seconds. So therefore, depending upon the type of application, we have to think of, we can say, different techniques. And effective techniques are that based upon IR, that is invalidation report, update report, hop-oriented cooperative caching, etc. These are reports which are or the techniques which are published in research papers in journals, and idea is that they will be sending or broadcasting reports related with the data, and if clients know they have downloaded or they have stored the data, and if those items have valued, new values of those data can be downloaded. Similarly, cooperative caching. So this is a scenario. Cellular network is a scenario where access points or base station, they are connected to the outside world through wires. But there may be purely wireless scenario where nodes, they may be fixed or they may be mobile, and still for the purpose of taking strategic decision or for getting the data, they may cooperate, and different techniques of caching are there. We talk of cache data, cache path. Again, these techniques, they are part of, you can say, research papers already published. So there are, you can say, different applications, similar application scenarios where the concept of caching is being used, and it has proven effective for the purpose of, you can say, providing better and faster services. When we talk of, you can say, wireless sensor network, so I have taken a similar approach which is already published by some other authors, that is called NICOCA node importance based cooperative caching, where given wireless sensor network, they have translated or transformed that network into a graph. Now in the graph we do have, you can say, nodes which are connected through links, and link equivalent link will appear in the graph if two nodes in the sensor network, they are within the transmission range of each other as part of the WSN. So graph is there. Now some of the nodes, they are having, you can say, strong connectivity with the neighbors, or large number of neighbors are there. Now depending upon how much edges are emerging at particular node, then importance of that node can be identified. Larger the degree of particular node in the graph, this means more number of neighbors are there, and that node is more important. For example, if we store data at that node, it will be able to serve more number of neighbors. And it is also important from perspective of, you can say, routing of data. If something goes bad with that node, or this node fails, this means neighbor also parameter has been calculated depending upon its connectivity of the so this method technique talks about cache storage, how to maintain consistency. So these three issues, they are addressed as part of this research. Now we have proposed a research that is called entropy-based energy efficient cooperative caching for sensors, and this technique is effective for multimedia data. Rather than taking, you can say, simple scalar data, we have considered, this is our own research, we have considered multimedia data, where generally static images, they are considered, and even if we talk of video, then that data can be translated into different frames. So again, frames, they are you can say, static images, so that way even technique can be extended for multimedia video kind of data. So given the network like this, for example, it may be deployed in any environment, different sensor nodes are there. So first, if we go for a research in this area, then we have to talk, you can say, different requirements, like how multi-hop communication can be done. So for that purpose, generally we go for what is called clustering. So whole network is divided into different parts, and that technique is called clustering. So clustering has been used here, a grid clustering. So given the network, you can translate it to different partitions are there. Now we have to ensure that from one node from the cluster is not really cluster. Now neighbors, they may be horizontally defined, vertically, or they may be diagonally defined. Diagonally, neighbors, they are at, you can say, larger distance, so maximum distance is taken along the diagonal. Now we have derived that if R is the transmission range of every node, so R is a fixed parameter, or this is the physical communication parameter of any node. For example, if you talk of, you can say, bigger nodes like our laptops, again this kind of scenario can be used. We are well aware that R is a given parameter. It may be few meters, say something in the indoor, it will be something at present around 70-80 meters, although the value is larger. So R is given, but whatever you can say, maximum transmission range. So D, the size of the grid, or the side of the grid, has to be defined in terms of R. So if we consider the constraint like sensor force, then this D has to be defined in terms of R. So D has an R over 2 in order to make two neighboring nodes communicate which are different neighboring nodes. Now, when we talk of cache management, so different issues like which are shown in different colors here. Searching has to be done, so then we have to go for cache index lookup. So different issues they are involved. Similarly, issues related with the replacement, etc. they are involved. So that way, different issues which are to be addressed in any caching mechanism, they are cache discovery, that whenever data request is there or some query request is there, look up for the data. So how to locate the relevant data, that is called cache discovery. Then admission control, we have to decide whether whatever is the data coming at node has to be stored or not. If it is to be stored, we have to decide based upon what is called admission control criteria. Now, if it is to be stored, then we have to decide whatever you can say mechanism depending upon the available memory. If memory is available to store the data, then of course it will be admitted as it is. But if memory is full, then we have to go for what we call as cache replacement decision. So here we have to identify the items which are not for example, say during research in whether the new lecture video is more important or the research paper is more important. So you have to create a space for that new incoming data, and accordingly you have to decide whether it is to be stored. So that is part of admission control. If it is to be stored, which item to be deleted, so that we can create space for a new data, whether simple data or multimedia data. So that is part of replacement. If you have stored data, whether that data is still valid or it has become stale or obsolete with the passage of time, then you have to plan its consistency mechanism. So consistency has also to be resolved. For example, we were talking about cricket score. So maybe whatever is the score, is it valid after 2 minutes? Whether weather forecast report which was downloaded 5 minutes, is it valid? Maybe that is valid, but cricket score may not become or may not continue to be valid after 2 minutes. Similarly, there may be research article which may be valid for you can say next 1 year, because a similar kind of research the so therefore, depending on the types of applications, between for addressing the parameter. So image kind of data. Now we have seen that in network processing can be applied. For example, if data is coming from different points, then whether that data can be processed so that we can reduce the volume to be transmitted to next node. So some effective techniques they are to be devised. Now say aggregation techniques like maximum, minimum, average, etc. over the scalar data, they are simpler. But how to identify that, okay, given out of 10 photographs or the face photograph, one which is most useful or carrying most of the information is to be selected. So for that purpose, we have taken entropy as a parameter. So entropy for any discrete random variable, wherein in case of images it is a gray value, can be calculated by using this equation. So it has been obtained through the research that higher the value of entropy, more is the information that is embedded as part of that image. So given say grayscale image, we can calculate HP parameter. Even given colored image, these values they can be calculated for every pixel for three components, that RGB, or even if we use another kind of model for representing the image, then we can calculate those values for those parameters, and accordingly we can calculate say entropy for the whole image. So whole image entropy can be calculated for color as well as this. And thereafter we can take decision. The entropy provides a good level of information to describe a given image. If all pixels and have gray or same color image, the entropy, even the gray values or intensity of color pixels, in that case entropy value will be minimum or it will be less. If variation captured is higher, in that case, on the other hand, when each pixel of an image presents a specific gray level or color intensity, this image will exhibit maximum entropy. If variation is larger, then value of entropy will be more, meaning thereby that higher the value of entropy, more information will be there in the image, and if lower is the value, the image is not so useful. Thus, entropy can be used to characterize the information contained within an image, that is multimedia data and wireless multimedia sensor network. So generally, such sensor networks, they are called multimedia sensor networks, and because they are wireless in nature, so we'll say that wireless multimedia sensor network. Application to caching is justified because we are interested to cache more important images, or if we have to capture single image, so more important image, rather than you can say storing multiple images, but that single image should carry most of the information. So they should be the most useful image or most useful set of images if we go for more number of images. So simple example is given here, given two images on left side and on right side. So here variation in pixels are less. We have finding similar kind of pixels, and therefore this image will have low entropy. But here if we add, you can say, different types of pixels, then entropy is larger. So this image on the right side is having larger entropy. If we add more number of variations in the pixels, the entropy value will be increasing. So therefore, if you talk of say image of any natural scene, whether grayscale or colored, more the information captured in the scene, more will be the value of entropy, and that way this analogy has been extended and we can compute the entropy value, and has been obtained that higher the entropy, most or more useful the image will be. Now, how the issues of or issues related with caching they are addressed. So we will take issues one by one. So first one is cache discovery. So sensor nodes may be like this, and we have already seen that we have to divide into different clusters of grid size, and accordingly a sensor node, if having some requirement of data, will first try to search in the local cache. If not, then it will search from its neighbors. And if it is not available with the neighbor, it will send the request via you can say maybe the central storage or the edge base. So therefore, the request will go to next node. If it is not available, then next node even will search within its neighbors. So this way it will, you can say, send the request, and if data is obtained with some of the node, it will be sending the acknowledgement, then it will be confirmed, and finally data will be coming to the original requester. So here the you can say data is coming or reaching at the node, it is waiting for admission control decision, and if it is data is to be admitted, then we have to, you can say, suitably discover the node, discover the data which is to be replaced. That is, the replacement strategy will be working. Another snapshot that how requests from SNI, which is sensor node, they are generated. Then it will go to next neighbor, and then from that neighbor, the cluster head will be broadcasting the request, and it will be say reaching all the neighbors. Then it will be confirmed, and then response is coming, and response will be given to the original requester. So that way, rather than sending the request to SNS, which is a source of data, and it may be far away located within the network, or even part of other networks, or outside the domain of the network. So therefore, rather than sending so much you can say volume for handling the request or messages, data will be serviced from nearby node, and that way we are saving over the resources. So this is how the discovery works. Then thereafter, admission control, and data is coming, whether it is to be stored or not. So any caching mechanism is complete if it addresses this control admission control mechanism. So in this proposed scenario, when a node receives the requested data, cache admission control is triggered to decide whether it should be brought into the cache or not. So we have based upon, you can say, how design is to propose and the decision at a node size to as number of invested, and node from where data is coming, and other is importance of data item. So if HI is less than delta hop away from the requester, then cache it, otherwise don't cache it. Meaning thereby, if data is coming from far away location, and those locations, they are reachable over wireless link. So in order to get data in the near future, again we have to spend in terms of communication, in terms of computing, in terms of maybe delays. So if data is stored, then it will be serving the requests, you can say, by costing less on these parameters. So therefore, the hop distance will be a critical parameter to be considered. For example, if data is coming from far longer distance, it is advisable to store the data. But if data is available in the nearby nodes or in the neighborhood, it may not be so useful to store. And if we are storing data which is coming from the neighborhood, it will lead to replication of data, because it is creating duplicate copies of the data. So therefore, we should avoid such duplications within the same cluster. Now with the small delta, the number of replicas for each item is high, and access delay for this data item is low. With a larger delta, each data item has a small number of replicas, and access delay can be longer. So admission control will be taking based upon, I can say, these parameters of count as well as usefulness of data. So usefulness of data, already we have seen that can be defined in terms of entropy. If entropy of the data which is coming, that is multimedia data which is likely to be stored, is higher than given threshold, we tag it to be useful data, otherwise it may not be so useful. So if it is useful data, it qualifies for storage in terms of hop distance, we will store it. So initially this say threshold value which is identifying the importance of data can be less, because we have large free storage, but with the passage of time, more items they will be admitted, and free value of the storage will be decreasing, and hence we have to gradually increase the importance parameter, so that only very important data value or data unit qualifies for admission control. That is the mechanism. So it leads to the theorem that higher hit ratio is obtained in a cooperative or cooperation cluster if nodes have similar access pattern and they cache more distinct items. This even intuitively holds true if similar access pattern is there. This means data requests are generated so not very or not of varying nature, but they are generated for similar type of data. This means if we store this data, then it will be useful in the future, not only from perspective of individual node, from also from perspective of the neighborhoods. So therefore, if access pattern is similar, it will be advisable to cache the data. And if nodes they cache distinct items, this means in the neighborhood different data is stored. Therefore, the future request for this different data can be satisfied, but this has to be from the access pattern. The analogy is something similar that, okay, if we have requirement of some data or requirement of something, then if I have obtained that particular item, if in my neighborhood other items are lying, maybe another neighbor is storing something different, then if I require something in the future, then I can obtain from the neighbors. So therefore, if they store or they maintain distinct items, then user requirement in the neighborhood can be satisfied from, we can say, or far large number of data items. So therefore, this analogy has been used in this caching strategy so that we can meet out the user demands, and accordingly we can make optimal use of the available storage. Then replacement policy. So if you see replacement policies which are existing conventionally, they are based upon, say, least frequently used, least recently. So depending upon frequency or depending upon the use of data, then depending upon the time at which it has been accessed. But such kind of strategies, they are not so useful in complex scenarios like ad hoc networks or wireless sensor networks. So maybe we have to do a multiple replacement strategy based upon parameters like importance, which is identified by using entropy, then popularity, depending upon how frequently we are accessing a data item. So we can calculate its popularity, then distance from which data is coming, consistency, whether data is consistent or what is the nature of data. So these parameters, they are taken as a multiplicative mathematical model, and we calculate a combined function called value for every data item. So a data item with lower or least value is considered as victim for replacement. So maybe we have capacity of 1000 or 100 data items. If new data is to be stored, which one to be replaced or to be deleted? So maybe one with least value is not so useful, and hence it has to be deleted so that we can create space for incoming data item. Now we talked about mechanism like how we can discover data, how it can be decided for admission, and thereafter victim is to be identified for replacement. Now when we talk of, we can say, handling the situation at present, and that too where movement or mobility is associated with the user, then there is, you can say, constraint in terms of resources. Sometimes we are available with strong connectivity. There may be some places where connectivity is not so strong, so can we automatically embed some technique within the system or within the node so that they can identify the future requirements and accordingly they can proactively prefetch the data as strong connectivity is available. So that is the motive. So here we can identify association among the items. For example, there may be, if we talk of research papers, then research some papers which are cited as references. So this kind of similar scenario can be thought in case of other areas like wireless sensor network, and we can identify association or associated data items. So some example is there. For example, D1 is associated with the D2. That is, whenever there is use of data D1, D2 also is to be used, and there is probability of 90% use, and whenever D3 is used, maybe D4 will be used or this will be accessed 40% of the times. Assume that fetching delay, because this is not a scenario where data is sitting at equal distance, as in case of say processor cases. Processor location is fixed and cache location is fixed, so therefore delays they are almost equal. But in case of wireless sensor network or wireless networks, any generic wireless network, the delays they will be different. For example, sometimes we involve, we can say, multi-hop, and those multi-hops they will be differing in number depending upon the location of the sender, location of the, we can say, requester, as well as service provider. So assume that fetching delays they are for D2 it is 2 time units and D4 it is 4 time units. The expected delay saving from caching D2 is therefore this 0.9, that is 90% into 2, and for D4 it will be this much. Now caching D2 item with lower fetch delay, those if we go with the, we can say, conventional techniques, then the fetching delay are to be considered. But here we are also combining it with the, you can say, probability or popularity of access. So caching delay associated with lower fetch data item is in fact more beneficial than caching D4, which are having higher, you can say, delay. So if we go with the conventional technique, then we will be caching D4 rather than caching D2. So if we are caching D4, then we are saving less as compared to if we cache D2. So therefore, this kind of association has to be identified depending upon parameters which are contributing for the cost of caching. Now, again, how association will be helping? Assume that access sequence as we considered in any conventional caching technique, maybe something like this: D1, D2, D4, 5, D1, and so on. Now association rule, assume that is association rule, we go into details of data mining, we can define some rules like this. That is, whenever there is access for D5, access for D3 will be there, and there are 80% chances of this. So assume this kind of association. Similarly, other kind of association we can assume. So if we go with a conventional technique, then say whenever there is no consideration of association, then we will be storing the data like this, and delay say hits will be D1, D2, and then D1, because D1 is accessed again, so there are 3 hits. But when we talk in terms of association, then whenever there is access for D5, this will store D3. So D5 is there, and accordingly D3 will be stored. So number of hits, if we find in this pattern, they will be increasing. So if we consider the association number of hits, they will be considering. This means we have to consider association among the data items, and based upon that, caching or prefetching of data has to be done. Now whenever association is found, then we assume that D5 is already in the cache, and whenever access to D5 is there, it implies that access to D3 will be there in the future. So we have to download or we have to prefetch D3. So if we consider this kind of prefetching, then we are doing proactive prefetching, and association can be done in order to identify the nodes, identify the items which are to be prefetched, so that way we will be saving on different parameters. So internal details have been worked. I will be skipping these details due to paucity of time, that how we can calculate confidence, and we can identify that how different items they are correlated. So given say access to data item X, we can identify some similar items which are to be, or similar data which is to be stored. So we can calculate set of data items which are to be stored, and items they can be prioritized depending upon their priority. For example, if we talk this kind of access, for example, if D1 is there, then there is likelihood of access to D2 with 80%. Similarly, if D3 is there, there is likelihood that D4 will be accessed 82% of the times, and so on. And if multiple accesses are there, that is two items, say D7 and D8, they are accessed, there is likelihood that 74% of the times we access D9, and so on. Now, depending upon whatever you can say strategy has been defined in this slide and the previous slide, we can calculate a prefetch set. So items they can be prioritized. D5 is there because it is appearing on the right hand side. Then similarly D9 is there, D2 is there. So we are having popularity of D5 in the future corresponding to this example as 86%, 83, 80%, and so on. So that way some sets called prefetch sets, they can be identified depending upon some learning techniques. Now these learning techniques may be based upon data mining, or we can apply some other machine learning or deep learning techniques. So we can identify the item or data which is likelihood to be accessed in the future. Now if we have say space to store only one item, then we'll store say D5. If we have space to store say two items, we'll store D5 and D9. If we have space to store say three items, we can store D5, D9, and D2, or we can prefetch them. Prefetching means before actual request is made for these items, the data will be stored, and that decision will be taken automatically by the system in the background based upon some tools which are executing that, okay, this requirement may be in the future, and the data will be stored. Something, suppose you are traveling on the highway and you are interested in looking information about some hotel or maybe a restaurant, then your system understands your profile, and whatever you can say, maybe the hotels, the information related to restaurant appearing on the along the highway, that will be downloaded automatically. So some tools or intelligent tools, they will be working in the background, and they understand the profile, and accordingly they will be downloading data. It will be presented to the user for decision making. So similarly, if we are using other application scenarios where sensor data is to be captured and it has to be downloaded, maybe in order to satisfy the future queries, data has to be sensed, and accordingly it has to be maintained for addressing those queries. So given the issue of how to apply prefetching, it not only is applicable to say sensor networks, but this technique can be extended to other domains, and depending upon say type of scenario, we can extend such sets to larger value, and if we talk of constraint environment, maybe we have to restrict to lower value, so that storage which is less in volume for sensor nodes, that can be used optimally. Then cache consistency, that how long the data is becoming or remaining consistent again depends nature of the data. So if we talk of, you can say, strong connectivity, like using wired network, generally we go for what we call a strong consistency. So as and when data is updated, it has to be communicated as latest copy to the nodes or the clients where data has been cached or stored. But if we talk of, you can say, wireless multi-hop kind of environment, like wireless sensor networks, so there we cannot go for strong consistency, and we have to go for weak consistency. So generally in this kind of scenario, we go for what is called TTL, time to live. That is, given the data value, we have to associate a factor so that this data is going to stay valid for this longer period. So that depends upon the nature of data, and accordingly we can associate consistency parameter, and if this parameter exceeds the assigned value, then maybe data becomes obsolete, otherwise it is still valid or fresh data. So some simulation has been done based upon these parameters, and different effects like network lifetime, carry latency, byte rate, so which are otherwise applicable to conventional scenarios also. They are studied. Then in addition to that, because energy is a critical parameter, so that needs to be analyzed, so they have been identified and analyzed accordingly. So given the scenario, based upon these parameters, we see that okay, graph after some time becomes saturate, or trends they become saturate. This means if we talk for selection of cache size, maybe this much cache size will be sufficient. Similarly, we have to take care of other parameters. So compared with the Nikoka, the technique that I described initially, then there is something similar technique. It is again proposed by us, but not using prefetching. So if prefetching based technique is there, and that considers multimedia data, it behaves best among these three. So cooperation and prefetching helps in better results. Similarly, say energy efficiency or energy consumption has been analyzed, and we are able to reduce it depending upon what kind of scenario. For example, we are not considering broadcasting and replacement, etc. That has been more intelligent as compared to conventional techniques. So therefore, parameters are better, or the results are better. So maybe in the future scope they consider or they may consider compression. Then we can think of, we can say, data aggregation, data fusion and aggregation, though they are used interchangeably sometimes, but fusion is different from aggregation. In fusion, we combine different type of data. For example, if some sensor nodes are say having multimedia data, in addition to that they are having capability of you can say scalar data like temperature, then multimedia data like image. So how these two data packets can be combined into single packet, so that they can be transmitted, and we can save in terms of say metadata, that is overhead to transmit the data. So a lot of saving can be done, so that volume of traffic is reduced. So similarly, the scenario can be extended to handle purely multimedia data, audio, video, rather than converting these parameters at static frames, so they can be analyzed. So that way research opportunities are there, and a lot of research papers and articles are available on the net related to multimedia handling in sensor network. Now, as IoT contains you can say or makes a lot of use of wireless sensor technologies, so these research issues, they are still open to IoTs, but IoT is a heterogeneous kind of environment, and these research issues, they become even more complex in terms of handling of, you can say, communication, computing, and more critically the issue related with security, because they are open network, there is no single ownership, and hence security issues, they are much more critical. in IoT as compared to even sensor network. And in sensor network, even these issues, they are critical because of wireless nature, because wireless is broadcast kind of network, and even key distribution, key deployment, they are issues for them. There is no solution, there is no well-defined algorithm existing at present, and maybe pre-deployments, they are to be handled, and dynamic key distribution is not possible at present. So this was all about, you can say, scenarios like wireless sensor network, then criticality due to large volume of data, and how we can identify techniques where we can reduce volume of data to be processed or to be communicated, and how usefulness of data can be established for future storage, and some techniques related with you can say caching, so that we can save the resources. So this is all about my talk. I would like to thank, and now we can have discussions.
Yeah, thank you, sir. Thank you for your so the long session you have taken from the morning till now. I request to all the participants, if you are having any question, you can ask it directly to sir, so that we can discuss it further. Yes, you can raise your hand or you can ask it directly. Yes, any question?
Excuse me, sir.
Yes, sir, please.
Sir, can we get PPT from our main? That's why we can study from this PPT at our home.
Okay, I will be sharing the handout, and that way you can have access to the PPTs.
Because when we get PPT, we can start from home, and we can lots of things can from PPT.
No, just you can ask the question, because otherwise it will be taking a longer time. So whatever you have noted down, accordingly you can post it.
Yes.
So that we can discuss it. Later on, I will share the handout. Okay.
Okay, sir. Okay. Thank you, sir.
Any other question from anybody? Yes, please. So waiting for 2 or 3 minutes. So if any question is there, so we'll wait for 2 minutes, sir. So if no question there, then let's see that everybody is satisfied with the self-answered. We shall be sharing all the PPTs or the handouts via mail only. So I'm collecting. Yesterday I collected too, and today also we'll share that also. And so.
Okay, thank you, sir.
Yes.
Thank you, sir.
Okay.
For sharing PPT.
Okay. So I will take it that there's no question from the audience. Yes. So I thank you, sir, for sparing your valuable time with a busy schedule. I request sir only 2 days back, and he never said no. So I was very happy to have you on this FDP on data sciences. So we discussed how we can acquisition of the data from the wireless sensor networks. And I hope that in future also we'll be having you on many other FDPs. Thank you, sir. Thank you so much.
Okay, sir. I'm also thankful to you for giving me opportunity to have interaction with you as well as with the audience. So thank you, and I hope we will, you can say, strengthen this, you can say, partnership.
Yeah. Sir.
Thank you.
Sure, sir. Thank you all participants. So we shall be Now starting the third session rather at 2 around. I'll be sharing the other details on your mail. Thank you all. Thank you.